morning, everyone. Welcome to the course, which we have organized in under PeneloPe and Mari4Yard project. Today, we will actually is the continuation of what we have learned yesterday, and we would like to give you a glimpse into different technologies which we are basically developing under this project. And the main objective is to reach out the different end users and also some students. So the main objective was basically to make it more in one end on the introductory side, like to give all the people at the different levels to understand, and then also to move a little bit more into the depth to make understanding for the people who are maybe a researcher who would like to continue working in this area. So with this, my name is Jabal Masood. I am a team leader here at AIMEN, and I will be assisted by this specifically about this course with my valued colleagues Isidro, Claudio, and Afra. So first thing first, I am basically representing AIMEN Technology Center, which is a multi-sectoral innovative and technology center located in Galicia in Porino, where we work mainly on the R&D activities. And the main areas of research are materials, advanced manufacturing processes, digitalization, and sustainability. We can see here also that our services are divided into two components. One is R&D and the other is industrial services. Yesterday, my colleague also have given some input in the same. So this project is basically this training is funded by PeneloPe and Mari4Yard project. These both are the European Union projects running at AIMEN as a coordinator. Here, for instance, in the PeneloPe project, as an overview, is basically a closed-loop digital pipeline for flexible and modular manufacturing. Whereas in Mari4Yard project, we are looking for portfolio of technologies ranging from collaborative robots to AR, VR, and also connecting to the small and medium shipyards. So if you would like to have more information about these projects, you can connect to the project website. I would like to take a couple of your minutes to give you a concept which we have been promoting and marketing at AIMEN. And the concept is called AIMEN Didactic Factories. What does it mean is that basically we at AIMEN are promoting our facilities for the training and upskilling capabilities of the workers. So what we think is that the new technologies which are going to be implemented into the industry, before actually they are going to the industry, we can provide the facilities to our stakeholders, students to come here and learn the technologies about. And that's one concept of didactic factory. The second one is basically on the purpose of Industry 5.0, where we would like to also demonstrate the concept of digital-centric solutions. So here, for instance, you can see on the right-hand side some pictures taken from our factory. So today I will be going through initially on the introductory collaborative robots and safety concepts. It would be further been elaborated by my colleague Isidro on the safety part, and then on SSM and collaborative application by our technology and the roadmap. You will understand what exactly these type of concepts are like. What are collaborative robots? What are their classifications? What are different type of standards they are up to? We will also talk a little bit, touch about the embodied robotics, where we can also look about see about the classification, their impact, the technology sectors, and the commercial products. Then we will go more into details about how to design the applications. So how to basically, what are the major two challenges which we see in collaborative robots? Then we will go through how to design the workspace. Then we will enter into the safety aspect, and further on we will then go through speed and separate monitoring and guiding, power and force limiting application, and then the take home message. So before starting, I think it's very important to understand that why we are going towards the human centricity, why we are going towards uh, the, the robots which the humans can touch, right? So that's basically comes from the need from the industry. From initially from the last decade, or like last few decades, we have industrial revolutions where we can have a big industrial robots working in the industries. However, there are some tasks which cannot be done by the big robots. And those tasks, for example, require the human dexterity and also the human capabilities or human knowledge. And in here, it comes the human worker as a cognitive system. And also the concept of Industry 4.0 and 5.0 are much into place, where we have a different type of digital concepts coming into play in the industry. So here, for example, different colors represent the different three domains, where we can see that on the perception, we have, for example, the enabling technologies, which comes from, and in sensors. And on the top, we can have the cognitive technologies. And on the right side, we can see in the green in the interactive technology. So what we are going to talk today is basically the collaborative robots and in this domain. So you can see that these are really highly multidisciplinary area. It's don't only require you like to focus only on one, but they are all connected. So when we talk about robots, when we talk about this, we actually talk about different enabling technologies working together as a system. And human is always in the center. So that's something which is very, very important factor. So coming with this point, why this type of enabling technology are one of the biggest challenges which we are facing today in society. Number one is about the aging society. So the human centricity is important that because we are aging, we know that in Europe, especially, we have faced the aging population. We have a skilled labor shortage, which means that, for example, if we are working in an industry, we don't have enough skilled workers who can continue working as well. So due to this reason, we require some sort of like inside the robotic technologies which can help. There is also a skill mismatch. For instance, with Industry 4.0 and 5.0, we are also seeing that there are new type of skills. So in the previous slide, you have seen there are different technologies working together. So we have a big skill mismatch as well in the industry as well today. On the technology front, we have rapid evolving technology. We have artificial intelligence also now, and also competitiveness and customization. For example, in different sectors, we have a lot of competition. For example, Europe is having a big competition with China, or for example, US. So we are in a very competitive environment. And on the industrial front, we have two factors which are worth to mention. One is the manual work. There's a lot of manual work still today in industry, especially in shipyards and in the big part manufacturing area. With still too many manual operations, we can see, and we can see also that there are a lot of manual operations which cannot be done by classical automation solutions. So we would like to focus there, and then the complex manipulations and high flexibility is also needed. So there are workers with special needs. So there are also in the industry there are workers with less skills, more skills. There are also workers who have, like for example, starting at the young age, or for example at the later stages of their career. So we have vulnerable groups also available in the industry. So the crunch of all this work is that we think that the new physical assistive devices are needed to help the industrial progress. And in this regard, we just go to the next step. So yesterday you have seen very interesting demonstration coming from my colleague Isidro about robot programming of the industrial robots, right? So what the industrial robots have been revolutionizing our industry for about now 50 years. And we see that these robots are very high speeds. They are, but at high speed, the one important factor which we are missing, that they are not very efficient in terms of energy. So this is one very important aspect, and the other part is that they are not safe. So normally what happens is that these type of big robots are in fences. You have to put them in under fences under very strict conditions. So the human cannot enter once the robot is moving. So that's one of the biggest barrier. The other big barrier is that yesterday you see one small program made by Sidro, and you guys touch the robot, you see how the program is being made. Just imagine that you have to be making all the program for a very big application. It will take you a lot of time in programming. So what actually is needed is some a bit of difference in this regard in terms of programming, in terms of safety, in terms of efficiency. So what we see that, for example, collaborative robots actually work not really fast. They are being designed to work at lower speeds, but relatively as we can reduce the speeds, we are more efficient in terms of energy. And then we are also more safe in terms that the human can touch the robot. It can manipulate from one position to another. It can, for example, the same task which we have done yesterday from moving from one position, making a square. If it is a collaborative robot, probably would be a bit faster because you can just move the robot from at this distance 4 points, and then you can get more faster response. And then what we think in the future would be wearable robots, which would be probably at the human speed. They will work, but they will be the optimal in terms of energy and the safety. So that's more or less the version which we think. And today more we will focus here on collaborative robots. So what collaborative robots are? The collaborative robots are referred to a robot with the capability of being used in collaborative operations. What does it mean is that there is a robot with integrated sensors. When a human would but subject touch the robot, these sensors are intelligent enough to detect that the human is touching. And in this case, what happens is that the robot can move or see the intention of the human. Of course, this is not optimal. There are a lot of limitations still exist, but the main idea is that the collaborative robots have the integrated sensors, which basically helps to detect the human in such a way that the human can touch it and can move into the collaborative operations. Very good. So the next part is that what are the type of different collaborative robots exist? According to the standard ISO 10218 Part 1 and Part 2, there are 4 different type of collaborative operations exist. What the first one is called the safety monitored stop. This is basically is the physical stop or like a cord which you can put on besides the robot. In the case of the speed and separate monitoring, here, for example, the system with the help of the vision systems or other sensors are able to detect the human and then adapt itself to the speed of the human and enter into the safety mode. In the case of the hand guiding, here we use an external interface that is most of the time is a physical interface where the human interact with the robot while moving this physical interface. For example, a joystick. And finally, a power and force limitation is mostly the collaborative robots in the market we see are designed for. You can see for the power and force. We will go more into detail later into each of these parts once we will at probably at the later stages. So that was basically the collaborative robots type. But there are also there are different types how we basically classify the collaborative operations in industry. That can be in three ways. One is called the coexistence. The coexistence is basically a type of collaborative operation where there is like a robot and the human. They exist in the same place, but then they are working autonomously. For example, robot is moving in one corner and the human is moving in another, and they don't have a very close link between them. In the case of the cooperation, what happened is that they cooperate to complete the task. For example, some part of the task is done by robot, some part of the task done by the human, and then they cooperate, but they don't interact during the task. Okay, and in the collaborative part, what happened is that human and the robot complete the task together. Okay, so if there is one small task, the human actually type the robot go to that part and complete it. So these are the basic concepts for the classification of collaborative operations. And then if we go to one step further, there are different type of interactions, right? So we have in industry, when we see the interaction, the standards give us different types. So in this case, we have two major types. The first is called the quasi-static and the transient contact. To make you understand, I just illustrate that. So for example, if a human and the robot is moving in the same direction and there is a way that the hand, or for example, the body part of a human is clamped between a robot and a fixed part, is basically a quasi-static. And in the case where there is a transient contact, like for example, if are moving into the different directions, is basically for example, if our robot is moving and you touch a robot, like, so this is basically a transient contact. So at this stage, if you have any questions online, guys, and also here, please stop me. I would be happy to answer your question. There is not a very fixed question and answer session at the end. So I would prefer maybe if you have some questions right away, please raise your hand and we can explain. So this slide is designed for the target audience, which is SMEs. So just to see why collaborative robots are relevant, right? So we see that from the market in 2022, we have 900 to 900 you can say millions of euros of which is basically in Europe is 30% of the global. In 2022 to 2030, what we see here is that the expected amount. So here, this is less than 1 billion, but here we are expecting something like 7 billion euros. Sorry, US dollars here. And this is very important because that's basically a prediction which we see in 2030. And then similarly, the market says, for example, that in terms of unit present is mainly on the pick and place. So you collect it and place it, the assembly. But in the future, welding and gluing and cutting applications are one which foresee by the researchers, market researchers, as one of the biggest applications coming. Then the payload capacity, I think if you see the market, up to 5 kilograms robot is 44%, and up to 10 and above are the other parts. So if you can see about the payload wise, there is also a lot of robots which basically are working for the low payload than the very high payload, collaborative. So what collaborative robotic technology says today? This is about enhancing human-robot interaction, flexibility and adaptability. This basically, the claim is that it can assist, not replace, on this philosophy, reduce workforce requirement, cost saving, and training and skill transfer. So these are the basic claims which say that, okay, if you buy a collaborative robots, these are the claims they normally have in the market. How the market look today? There are several. This is not an exhaustive list, but just for you to know that in market there are different robotic companies available. Where, for example, ABP, KUKA, and from Mika, then Denso, Rethink, Fanuc, um, Yaskawa, and then Universal Robots, Kamau, and then the list is long. I mean, I just put few here today, but you will see probably in the collaborative domain is the universal law. So I just like to give you a little bit glimpse of the embodied robotics, and then we will enter into again more technical sounds, for example, part which is on the safety part and the SSM. So in embodied robotics, what we see as we see that the technology is moving from collaboration and now moving forward, we see the first part, which is basically exoskeletons are the ones which we consider like as one of the embodied robotics, where exoskeletons are the devices that are wearable, which can support and assist movement or augment the capability of the human body. So these are the type of robots which can be worn by the human. So you can consider them as those devices. So in the you can see here a device which is can help the human for maintaining or holding a cutter, or and here for example this is a device for example for maintaining a grasp, and this is a device for example used for the loading and lifting tasks. The classification of this type of devices are passive, active, and quasi-passive. Passive devices are the ones which don't have the external source of energy to drive the joints. Active are the ones which have the energy, for example, either electrical or hydraulic, or quasi-passive are the ones basically don't have the external energy source, but what they do is that they have the onboard sensors. So with your motion, they can actually charge those sensors, and then you can power, for example, your devices. Um, I would just very quickly go through the market. We see also that there is a big potential in the market at this moment. 27% was focused on the shoulder, then trunk, hand, arm, and legs. These are the body parts where you can wear these devices. Then you can have from 2017 onwards, we can have some market. You can see also in old terms, we can foresee increase in the usage of these type of devices as well. So the technology claims of this type of devices are to reduce musculoskeletal disorder, improve posture, assist nor replace, retain aging, skilled worker, improve productivity, and then improve turnover and increase job quality. In the market, you can see some devices coming from the hand and exoskeletons. Then for the arm and shoulder, here is a trunk and back, and then the leg support exoskeleton. Where we can use these devices are in manufacturing, in agriculture, and maintenance. Here there is some list where, but for example, maintenance the posture in the assembly line, or repetitive task loading and unloading, order preparation, and augmentation of force or limb. Similarly, we can see that for agri-food, there's exists some potentials in pick and place, harvesting, order preparation, and augmentation for force. And similarly, for maintenance, we have teleoperation, virtual and augmented reality, teaching and skill transfer, and augmentation of force. So if you would like to learn a little bit more in depth, technically, you please refer to one of the courses which is being organized under occupational exoskeleton for assisting by our valued partner in Mari4Yard project, and you can you register yourself with this. So you can learn much more about exoskeleton, how they are, how, and also about their contribution into the Mari4Yard project. So now coming back to the collaborative robots again. In the market, if you see in practice as well as in literature, you find there are major two challenges affecting the collaborative robots. One of the challenge, the first one is finding the best use case. So it's very difficult, for example, to find the best use case for collaborative robots. You can say that, okay, here this could be a use case where you can use a collaborative robot, but on the other side, when you apply the collaborative robot, you see that maybe it's not 100% work here. So what is how we can actually make sure that we are finding the best use case. And the other important factor is safety, because even though the collaborative robots is defined for the same important aspect that it can be more safe, but safety is one of the biggest barriers also we can see in the implementation. So these are the two major challenges we see, and we will now first we'll go through the finding of the best use case, and then we will enter into the safety part. So uh, besides safety, there are the six key challenges we see that, for example, proper configuration, selection of the given use case, manual skill learning and translation, collaborative design tool, cell layout optimization and scalability, tool optimization design, and the human robot collaboration scoping. In this case, for example, what stakeholders, for example, can do to overcome these challenges is to analyze and define the manual task map. What does it mean? Is that before going to select technology for a use case, they can analyze and define the manual task map, means divide that task into small steps. For example of manual pick and place, fruit pick and place is that, for example, when you are collecting and you are, for example, using a collaborative robot for this type of task, you divide it like into small chunks, and then use the number of man hours and sequence of the task. So it's here you are basically comparing what exactly you have at this moment with your man hours, and then you can compare at the first stage that most of the time my experience is that while dividing these tasks, you actually solve a lot of problems. So it's very important to first of all see to your use case and divide it. Then begin the task, robotic task map. What does it mean is that, for example, maybe robot is not going to do complete task. Maybe some sequence of the task starting where the robot will be useful. So it is important to identify the task based on their impact on the involved worker, production, and environment. Define the high-level task map. Here you can combine what the robot can do and what, for example, the human can do. And here, for example, the important terms which we used before was coexistence, cooperation, and collaboration. Maybe in some parts you can do have to do the coexistence. You don't have any other solution, so you need to maybe have other type of robotic solution. Then you have the cooperation. Maybe some tasks required that the robot will be working on one side and the human, and then they cooperate to complete a task. And then there are some tasks where you can choose the collaboration, where you can move the robot to that important that the area of interest, and this way you can, I think, define the high level task map and then define the layout, and at then you can define the layout and find the both like hazard and perform risk assessment. What does mean is that when you are introduce a technology, you should at that time also maybe are lose or not having a vision of some risks. So risk assessment and identifying them are one of the important factors to consider again. So I think from my point of view, these can be the 3 or 4 points which are important for designing a better use case. And after this, you can consider using a collaborative robot, for example, because most of the time what happened is that you have a problem and you take a robot there and then you try to find a solution. It's more important maybe to analyze the use case in better way and then go to the different solution. So with this part, then like to introduce now to the next challenge, which is the safety. From the safety part, I would initially go through 3 slides where I will explain concepts about the main safety, and then we will enter into into, for example, like what I have been discussing before, the type of collaborative robots. And here, the safety pyramid consists of three important concepts. First is to eliminate, which refers to physically removing a hazard. So as we see in the previous slide, and risk assessment and hazard analysis is very important. So here you should physically remove the hazard. Engineering control is which incorporate programming, safety, curtains, rails, or what type of engineering solutions which you can include inside the use case. And finally, we have the enterprise control, which changes the way an operator work through work instructions, restrictions, etc. The point is that enterprise control is quite difficult because it requires high management all from the top to incorporate the idea of safety. And here, for example, you have most of the time you may need to change the workstation altogether. So ISA on some standards which work on the collaborative domain. This is not an exhaustive list again, but the most relevant are these. And ISO 10218, IS part 1 and 2, then 15066. And then there is these two very interesting initiative at Europe, which actually cover toolkit, which actually work with the collaborative robots, and Eurobench, which basically define the test beds and the performance indicators. So here I would like to again go back to the first slide here, but I have defined the four concepts, which was safety monitoring stop, speed and separate monitoring, hand guiding, and power and force limitation. My colleague Isidro is now going to explain the safety monitoring part. Thank you.
Thank you. Can I stay here or I have to be there? Right. Thank you, Joab, for your great explanation about the collaborative robots and exoskeletons. Very clarifying and very complete overview of these technologies and safety measures and safety rules. Now I'm going to present you in this part of this training session classical safety devices in a robot cell. The content of this training, of this information is divided into 2 points. Conventional safety devices is the first one, with the mandatory devices, which should be always installed in a robotic cell. Additional devices will be defined as well. And I will show you some new emerging devices regarding the safety inside of a robotic cell. So, starting with the first point about the conventional safety devices, the mandatory ones. As Javad told, there are some risks regarding these kind of robotic cells with a lot of risk that should be avoided. Of course, these risks are the most of them impossible to avoid. So to minimize these possible hazards to be eliminated, we have to use these mandatory. I prefer to put mandatory devices regarding this robotic cell, which are the ones I'm going to explain you. These three devices, the first one should be the emergency stop buttons. This kind of device is intended to stop the robot or any other machine regarding the production process inside of the robotic cell. It works when the human operator press on this button. So an electrical circuit, the safety circuit, is usually closed, but when this button are pressed, this safety circuit is open. And this by the safety digital controller, which acts in accordance with this axiom, stopping all the devices, of course, the robot as well, connected to this safety digital controller. How does it act on the robot or in any other machine is disconnecting all the energy that arrives to the robot or the machine, like electric power or hydraulic or pneumatic power. Of course, when it happens, the robot and the machines stop immediately. These kind of devices can be actuated, of course, by the human operators, pushing them. When we want to arm them again, what we have to do is, with a conscious movement, we have to pull, or sometimes as well, we have to pull and turn around or not, depending on the device. These emergency stop buttons are usually installed in different points around the robot itself, usually outside, to be manipulated by a human operator, as I told before. And of course, it depends. The quantity of them installed depends on the robot itself, if it's big or it's not. But usually, we have to have at least one working. Usually, they are installed beside the robot cell doors. The second device I want to notice you is the emergency stop course. That is like their function is just like the emergency stop buttons, but opening on a safety circuit controlled by the safety controller. But they have the advantage that they usually installed. They are installed inside of the robotic cell, all around the perimeter of this robotic cell. So it's easier to reach at any point inside of the robotic cell the action to stop the robot or the machines inside of the robotic cell. To do that, a human operator should pull from this cord, and that's enough to stop our machines inside. They are usually installed when, for example, in conveyors in robotic cell where a conveyor is working or a gantry is working. Okay, because of the length of these bigger devices. And the last device regarding these mandatory devices is the 3-position enabling device, which is a device usually integrated in the robot teach unit, which is handled by the robot operator, which is working besides the robot when, for example, during the maintenance tasks or during the programming task, when this robot operator is working beside the robot cell. And how does it work? This is a device that when the robot operator is not present yet, the device is released. So safety circuit is open. So the energy to the robot motors is not able to reach this robot motor. So the robot remains stopped. So can't move. When the robot operator wants to move the robot, what it has to do is to press this device slightly to get the second position, which closes the safety circuit. And so the energy arrives to the motors of the robot and the robot operator can start to move the robot from one point to another one for programming task or something else. If during this operation there is some kind of accident, for example, there are two options. The robot operator could release this device, or in some other conditions could happen that the robot operator could press with bigger effort on this device. So in both of them, the circuit is open, so the robot stop immediately. Or any other? No. This is just regarding the robots. I will go to say that any other machine, but it's not. It's just regarding the robots. And this device is just working in manual mode, in the reduced speed mode. It's not working during the automatic mode, but because it's supposed that there is not robot operators working beside the robot in automatic or fast speed mode. So it's just for manual. These are the mandatory devices that we could find at any other in any robotic cell, in any common robotic cell. Now I'm going to give you some overview of a few of other safety devices that we could find besides the other ones inside of the robotic cell. The first one, of course, is the physical wall fences. Usually, when we have a robotic cell, we have to protect the entrance of anyone, of any person inside of this robot cell working space area, or to avoid as well something to be thrown out from this working area because of something that is happening wrong, or a mistake or something like that, or maybe because the process is a dangerous process like laser or welding, because of welding classes or some gases that are not that are hazardous, etc. So usually this is the first safety measure about in a robotic cell that we could find as well. Besides that, if there is a physical wall fence, usually, as it's normal, we should install as well some entrances to go inside of the robotic cell. So to avoid anyone could pass through these entrances, we should protect them with, for example, doors. And to avoid these doors to be open or closed and someone open and go inside, we should protect them with a safety door switch, with or without interlock, of course, it depends, but it's something advisable. And these kind of devices, what detects, it's when someone opens or closes the door. If someone opens the door, usually the robot, if it was working in automatic, suddenly stop to avoid any dangerous to the people who is going inside, for example. How does it work? Really is a kind of several buttons and handles besides the door. There are two parts. It's composed by two parts, female and male part. The female part is installed usually in the fixed part. The male is on the door. When the door is closed, both of them are together, the male and female. But when the door is open, they are disconnected. This action is detected. So the circuit, which usually is closed, the safety circuit is open now when the door is open, and this is detected by the safety controller. So the robot or any other machine associated will be stopped. Of course, this is a safety device to avoid any dangerous when the robot is working in automatic. In manual, this is concealed, of course, because there are other devices like the 3-position switches I mentioned before. So continue. Okay, when we have some entrances in the robotic cell, as I told you before, well, we could protect them with doors, but when someone, a human operator, should usually go inside and outside very often, the most flexible or the most convenient is to install not a door, but a safety light curtain. This consists of two devices, a transmitter and a receiver, faced off each other, covering the whole entrance space, and it's able to detect if someone or something is crossing this light. So when it happens, the robot usually stops working, usually in automatic mode. Of course, this is another device to be used when the robot is in automatic or fast speed mode, not in manual. This in manual is concealed. And once the curtain is free again, the robotic cell can be resetted and start again with the robot in automatic, pressing a button somewhere to robot working resumes. Something, another device, a little bit more versatile or flexible is the laser scanners. This kind of device as well is intended to protect the robot working area, like the curtains before. But how does it work? In that way, the surveillance area can be defined and parameterized in such a way like we can see here on this bottom right picture, where a robotic working area was defined, just the space that has to be checked if someone or something is going inside of this red area. If something is going inside or someone, then is detected by the laser scanner and the robot should be stopped. What else about this? Oh yes, how does it work, this technology? This technology is regarding the time of flight of a laser beam, which is emitted in a rotatory way, like a radar, creating a surveillance surface. So these both safety measures are working always. The light curtains and the laser scanner are always working on to detect to protect a surface in a plane, right? It's not a 3D detecting. So these are some of the additional devices we could have inside of a robotic cell besides the mandatory I told you before. Okay, this is the point 2, not the point 1, about the emerging safety devices, the new trends of safety devices are appearing constantly as off-the-shelf devices to be purchased. And I'm going to talk about 2 of them. The first one is the safety radar. It works like the laser scanner I explained to you before. But in this case, it's able to detect someone or something entering in the protected area in a 3D space. It doesn't work in just only in one surface, in one plane. But this technology is not using a laser like a radar. is using very low energy radio waves that detects micro movements of the people entering or working besides of this sensor. This technology is composed by two units. We need to buy two kind of devices, at least one smart sensor, which is responsible to detect people or objects using these radio waves. This information should be transmitted to the control unit is responsible to read this information from at least one of these devices, as well is able to read information from other digital signals, for example, pressed buttons for muting or reset, etc. And this control unit, what it's going to do is to enable the robots, switching them on or off, depending on the circumstances. This is the first device. The second one I want to teach you about this is the safety eye. This is as well like the other one, a 3D technology safety detection, detecting a volumetric space. If someone or something is invading the monitored area. To work with this, in this case, we have to purchase three different devices. The first one that should be installed on the top of the robotic cell, inside of the robotic cell, or almost inside, but in the place that it's supposed that the operator or human operator could go inside of the robotic cell, is the sensing device, which is on the top here. This sensing device consists of three cameras which supply the image data of the phone that is to be monitored. Okay. The information from this sensing device is sent to the analysis unit, where this data is evaluated, and depending on the results, these results can be sent to the programmable safety device and the control system that is the next device that acts like a safety PLC, which is able to control all this information from the analysis unit, but as well all the information from any other devices like reset buttons or indicator light units, for example, in that way, etc. And of course, to act with safety signals over the robots or other machines working inside of the robotic cell. So this is an overview from my side, an overview of all the safety devices regarding a robotic cell. If you have any questions, something like that, you can go ahead. Feel free to do. Nothing? Okay, so we can maybe follow with the next, with my workmate Claudio. Okay, he's going to explain the next.
Hey, my name is Claudio Sanchez. I'm going to talk a bit and discuss about how the speed and separation monitors method works, and what I'll describe a bit our implementation here in AIMEN's facilities. So first is to review a bit about the concepts that are around the SSM method. Typically, in an industrial robotic cell, the robot is surrounded by all the elements that are necessary to do the job. Usually, as my colleague Isidro and Tebat mentioned, there is a fence around this cell. So with this cell and the other elements for safety, it's not allowed any kind of collaboration between humans and robots. This space is usually called operating space, so where people are not allowed. So if we want to human and robots collaborate together in the same time, at the same time, we need a more open space that enables this collaboration. And this for this space is usually called collaborative workspace or shared workspace. Okay. So there is different methods that allow this collaboration. We will focus in this presentation in speed and separation monitoring at the SSM, but other methods like power and force limiting are also good for this objective. One of the important things in the power and force limiting is that this method waits until there is contact to limit the power and the force of the robot. This is not the case of the SSM. We can act in advance, detecting people in the collaborative workspace. So this method is based in measuring a protective separation distance between the robot and the humans here. So now I will explain how can we measure this distance. So the thing is that we have the physical reality here, and we need to create some model that represents in a digital realm the robot model on one hand and the human models on the other hand. As you can imagine, it is very easy to create a digital model of the robot in real time using the CAD files of the robot and measuring the inner sensor of the robot that provides information about the position of the joint states. But this is a bit more difficult to create human models in real time. So I will talk a bit about how are the different possibilities and how we implemented it here in AIMEN. So some of the advantages of the SSM method over other methods that is better in terms of productivity, because measuring this distance, we can establish some thresholds to make one. The first one is where the robot can operate at normal speed. The second one, and the one is the one who makes the robot slow, but it keeps working. That's the reason why is the best in productivity, because the robot never stops. And if the human is closer, of course, the robot stops. And also, this method is not exclusive. It can be combined with the other. Okay. So in this slide, I will present some of the methods that we work to detect people in the collaborative workspace. Our first approach was to use this technology, the ultra-wideband. This technology consists in a tag that emits a signal and some antennas around the fence of the collaborative workspace. The antennas can measure the power of the signal, and having different measures, we can triangulate the position of the tags in the space. Some of the advantages of this method is very cheap, it's very low consumption, and it's cheap, and the range is very large. The problem with that is the accuracy. We are measuring errors with more than half meter, which is a lot. And also, when you are using this method, you are only tracking one single point, only the tag. But the tag can represent the position of the person, but it doesn't represent how the body is in the cell, where are your hands, where are your legs, and this is very important in a robotic cell for collaborative jobs. So how can do that? Maybe basing the detection in computer vision. So using industrial cameras that provides RGB images in real time, we can detect the people, but some of the problems of this technology is that it's sensitive to environmental factors. The main one is the lighting condition that can affect a lot, and also the dust in dirty environments. And also, this method suffers from occlusion issues if the person is behind another object. It's not possible to detect it. From the software side, we have the OpenCV, which is a open source library for computer vision that allows us to manage the information that provides the cameras. So at this point, you may wonder how can we detect people in a 3D space only using two-dimensional cameras. So for that, we can use two cameras and create an stereo vision system. Okay. So this method allows us to have a depth perception and to recreate, reconstruct the environment in 3 dimensions. You can see here the two cameras in AIMEN's installations. Maybe you see the both pictures are very similar, but if we compare pixel by pixel, and if we know the relative position of the cameras, we can calculate the correspondence between pixel and pixel doing some maths. Some of the limitation of this method is the range, because you have a better accuracy here when you are detecting here your image. Further, the accuracy is worse because in these points both pictures are very similar. So the closer is the best. Okay. One important thing in computer vision systems is the calibrations. I will explain now two different calibrations that are mandatory to do. The first one is the intrinsic calibration. Doing that, we want to avoid the distortion that produces the lens in the image. Okay, in order to take let's say a plain image. This is very important for a correct image interpretation. OpenCV can do this job, and you can see here during the calibration process with a good calibration and with a bad calibration. These color lines, they are like this. It indicates that the calibration is okay. Something I already mentioned before is the extrinsic calibration. With this method, we want to calculate the relative position between the two images. Okay, so doing this process, we can have that position distance and also orientation. Okay, so when the stereo vision system is calibrated, we are using this tool. It is called YOLO. It's a neural network tool that it allows to detect images, objects or people in images. We can classify them, we can do segmentation, do tracking, and also start position if there is some human body in the image. This tool provides us accuracy results in real time. It works very well it's as any other computer vision system, it suffers from it's sensitive to the environmental conditions. Computer naturally is very intensive, so you maybe probably you need a GPU to run it. And also, we also detect some problems detecting small objects or objects that are at different scales in the same image. But this is a very interesting tool for our purpose. This is some of the results that we achieved here in AIMEN. You will see this in live downstairs when we were downstairs. So you can see here that when we did detect a person, we draw these bounding box around the people in the cell, and after that we can start the pose of the person. Something that is very important is that the system is able to detect multiple people in the cell, not only one. And the other thing that I want to highlight is that even we have partial occlusions, the system is robust enough to detect the person. Okay. You will see in more detail downstairs. Now the detection of people is solved. Now I want to talk about how can we create digital models for measuring the distance. So for this purpose, we are using this flexible collision library, which is a C++ library that performs some maths around creating solids and measure distances, visual detection, this kind of job. So using this library, we can take the points of the human body that the previous module detects, and we can create a solid that surrounds all those points. And with the model of the robot, we can iterate this over these solids and measure the distances between humans and robots. Now I will explain a bit about the architecture of this technology. Everything is done with the ROS, which is the robotic operative system that is a very important open source framework for robotics. It is the most popular, and there is a big community behind that, creating drivers, tools for assisting software development, getting. There is also possible to represent 3D objects in a graphic user interface. There is tools for simulation, but one of the main features of this framework is that we can share information between modules through messages. So this is more or less the architecture that we have, and we created one of the modules that is in charge of detecting and extracting the model of the people, and within the real-time joint space of the robot, and with the CAD file, we can extract the robot model. So with this information, the SSM module with the free collision library can perform and measure the distances between the two models. Okay. So when measuring this distance and comparing to the threshold I already mentioned, we can send the signal to the robot controller to run, stop, or slow the robot. This system works in real time. The cylinders adapt to the position of the body of the person. If the person extends their arms or even jumps, you can see how the cylinders adapt to the position of the body. And well, the measure is taken in real time. So that's all from my side.